Assalamualaikum and very good afternoon. Today we are going to continue with the second part of chapter 6. We're discussing on Butterworth filter design. The steps to design a Butterworth filter is basically more or less the same as the Chebyshev filter. As mentioned in the comparison between Chebyshev and Butterworth, designing process of Butterworth filter is a bit more difficult if compared to Chebyshev filter. And even in the circuit realization, Butterworth filter circuit is a bit more complex if compared to Chebyshev filter. So the design process starts with determining the number of filter order. Please make sure you refer to the correct appendix for Butterworth filter. So this is the example of Butterworth filter equation. The second step, you need to identify the omega c, the cutoff frequency. So in this case, you need to determine two cutoff frequency values because there's two equations for omega c. Next, you need to identify or write the normalized and real transfer function. And you need to refer to Butterworth coefficient or polynomial from the table. And lastly, circuit realization. In this course, the circuit realization for Butterworth will not be discussed in details. However, the steps taken are more or less the same as Chebyshev filter. As in the Chebyshev filter design, so you need to calculate the order number, the filter order number based on the equation. You can refer the equation from the appendix. So please make sure you choose the correct types of filter, either it is Butterworth or Chebyshev. So in this case, for Butterworth filter, the filter order number n is given by this equation. So same as in Chebyshev, so alpha s should be in dB. So you just need to key in the dB values without the negative sign. So this is alpha p, the passband gain also in dB. So omega sn again it is not equal to omega s. So omega sn is the normalized angular frequency. So you need to refer to the table depending on what types of filter you have. Either it is low pass, high pass, band pass, and so on. Next, you need to calculate the omega c. As mentioned earlier, there will be two omega c values in Butterworth filter design. And then you need to validate with alpha p and alpha s, or the passband gain and stop band gain, in order to decide which omega c to be used in the final design. So the equation for omega c can be found from the appendix. So for example, for omega c1, the first option for omega c is using the omega p, the passband frequency, and also passband gain. And please take note here, 1 to the power of 1 over 2n. So please make sure you calculate this properly. And the second option to calculate omega c is using the omega s, the stop band frequency and stop band gain in dB, and this is in radian per second. And again, this is to the power of 1 over 2n. So lastly, once you have omega c1 and omega c2, so you don't know which frequency to be used, which cutoff frequency to be used, so you need to validate those values into alpha p and alpha s equation. So alpha p is passband gain and alpha s is stop band gain. So meaning that by using omega c1, so you need to calculate alpha p1 and alpha s1. So using omega c2, you need to calculate alpha p2 and also alpha s2. Then you need to compare the calculated gain with the specification stated in the requirement. So from there, you'll see which gain that fulfill the requirement. Therefore, the omega c will be chosen. Okay, once you have the n, the filter order number, then you can write the mathematical expression of the normalized transfer function. So h and s representing the normalized transfer function, and letter u can write the real or actual transfer function given by h, s. Okay, so as usual, to convert from normalized transfer function into actual transfer function, so you need to refer to a table, the frequency transformation table. So from that table, you will notice that the s in the normalized transfer function will be modified or transferred into a new equation depending on types of filter used. Okay, let's look at an example on Butterworth filter. So design a Butterworth, okay, stated clearly a Butterworth low pass filter. Okay, so you can illustrate this using frequency response, filter response. So this is in dB and this is your omega in radian per second. Okay, so it is a Butterworth, so it is low pass, and so Butterworth having flat top signal, and then the cutoff frequency, okay, and it attenuates at higher frequency. So in this case, a passband gain between 1 and 0.891, so -1 for omega 0 to 10, so omega 0 to 10. So this is omega p equal to 10, and then at this point your passband gain equal to -1. This is your alpha p, okay, and then your stop band -30 dB, for omega s equal to 20, and then alpha s equal to -30, and then your cutoff frequency as usual at -3 dB, in which you have your omega c. Okay, so this is your -3 dB. Okay, so this is the filter response or frequency response of the given filter. So the first question asks you to calculate the order number. So you need to refer to the equation to calculate n, and then sketch the magnitude response. Okay, so sketch. So this is basically the filter response. So you need to sketch it properly, label all axes and the values involved, the gain and also the frequency, and then determine the normalized transfer function, and lastly the real or actual transfer function. Okay, to calculate the filter order number n, so please make sure you refer to the correct equation. Do not use Chebyshev equation. So in this case we have Butterworth, so please use Butterworth equation. So n equal to the following equation. So make sure alpha s and alpha p is in dB, and omega is n. Please refer to the table. Okay, so from the table, this is low pass filter, so Butterworth. So for low pass filter, omega s n, so omega s n equal to omega s over omega p. So omega s n equal to omega s over omega p. Okay, so replace all values into the equation. Okay, as I always mention, write down the general equation first before you put in any value. So this is the general equation from the table. Please write it down, and then write the equation for omega s, omega p as well. Omega s n, so it's equal to, so omega s in this case is 20, and omega p is 10. Okay, so put in all values first before you get your final answer. So this is alpha s. It's alpha s from the statement equal to -30 dB, and then alpha p equal to -1 dB. So in the equation, you just need to key in 30. Okay, 30, and alpha p equal to 1. Okay, just ignore the negative sign post. right? So then you calculate the n equal to 5.9569. So as in Chebyshev, you need to round up the n to the next higher whole number. Therefore, in this case, the n equal to 6. Okay, so the second question asks you to sketch the magnitude response of the filter. So as stated, it is a Butterworth, so it is flat top. Okay, it's flat at the passband area, and then it's attenuate at omega s, right? So please label all values alpha p equal to -1, so don't forget the axis in dB. So this is supposed to be -3 dB for omega, the cutoff point. Okay, and then label all frequencies as well. Okay, next, the third question, determine the normalized transfer function. So as usual, refer to the table for Butterworth. So for Butterworth filter, the normalized transfer function given by this equation. So we have calculated the n equal to 6 from the first question. So you need to rewrite the equation into the general equation using the n values. Okay, and then followed by the A. The A is the coefficients of polynomial for Butterworth filter. So how to get the A values? You need to refer to the table for Butterworth. Please make sure you refer to the correct table, Butterworth filter, and n in this case is equal to 6. Okay, as mentioned in Chebyshev, please write down the coefficients. Okay, write down the coefficients before you put in the values into the equation to avoid mistakes. Okay, so list down all polynomials, and then you can replace these values into this general equation. Okay, then you get your normalized transfer function. Okay, next you need to determine the final transfer function or actual transfer function. So you need to refer to table F.5, which showing the frequency transformation of a filter. So this is a low pass filter, and please make sure you get the correct equation, okay, the right equation. So on the left hand side is for Chebyshev, and on the right hand side, as stated, it is for Butterworth. So in this case, all s will be replaced by s over omega c. Okay, so this is the normalized equation. So all s will be replaced by s over omega c. But what is omega c? Okay, so we haven't calculated any omega c yet. Therefore, you need to refer to the appendix for the equation of omega c. Okay, this is the equation shown from the appendix to calculate the omega c. As mentioned earlier, for Butterworth, you have to calculate two omega c values. The first one using the passband information, and the other one using the stopband information. Okay, so you need to calculate omega c1. So we call this one as omega c1 and this one omega c2. All right, and then you need to have the requirements, the filter requirements in hand, so that you can compare the values with the specification. All right, so omega c1 equal to this equation. So omega p from the statement, this is your passband frequency. So this is your omega p, and this is your omega s, and then this is your alpha p, and this is your alpha s. Okay, so key in all values in. So please make sure this is 1 over 2n. Okay, so n in this case equal to 6. So you get the first omega c equal to these values. So this is omega c1, Next, calculate omega C2 by using the stop band information, omega S and alpha S. So you get omega C2 values. And yet you still don't know which omega C to be used in final equation. Okay, so from earlier calculation, you have the two omega C values, so omega C1 and also omega C2. So in order to choose the suitable omega C or cutoff frequency, so you need to apply both omega C1 and omega C2 into alpha P and alpha S equation. Okay, so meaning that you need to calculate alpha P1, so you need to calculate using omega C1, calculate alpha P1 and also alpha S1. Using omega C2, you need to calculate alpha P2 and also alpha S2. Okay, so let's calculate. So alpha P1 equal to, okay, so you replace alpha P1 using omega C1. Okay, to the power of 2n, n equal to 6. So omega P equal to, from earlier statement, omega P equal to 10 and omega S equal to 20 radian per second. Okay, next, calculate alpha S1 using omega C1. Okay, so alpha S equal to omega S equal to 20, so omega C1 11.1919. Okay, so calculate alpha S1. So you get the values in dB and convert it into linear. Why do you need to convert it into linear? To ease comparison with the filter requirement. Okay, once you have completed alpha P1 and alpha S1 using omega C1, now proceed to calculating alpha P2 and alpha S2 using omega C2. So this is your omega C2. So calculate alpha P2 and also alpha S2. So now replace the omega C with omega C2. Okay, now it is omega C2. Right, so calculate alpha P2 equal to this value and alpha S2 equal to this value. So to convert this into dB, it is equal to 20 log of x. So this is your x. Okay, so the value in linear. Okay, once you have all the values using two omega C values, then you have to decide which omega C to be used. So in this case, you need to refer back to the statement or the filter requirements. So the passband gain, meaning that alpha P must lies between 1 and 0.891. Okay, that's why I think it will be very good to have your dB values converted into linear values, so to ease comparison. Okay, so check one by one. So the alpha P must be in between 0.891 to 1. Okay, so using omega C1, you get alpha P equal to 0.8913. So it fulfills the requirement because it lies between 1 and 0.891. So we tick that one. Okay, so check alpha S. So alpha S must not exceed 0.0316 or negative 30 dB gain. Okay, so check the alpha S1 with 0.03069. So it is less than 0.0316. So it is not exceeding the required value. Therefore, this is also pass or fulfill the requirements. So let's check for omega C2. So alpha P2 0.896. So it lies in between this value. So this also fulfill the requirements. Now let's check for alpha S2. It is 0.03162. Okay, so it is not exceeding, it is exceeding the requirement a bit. Okay, it exceeding the required value because the required value is 0.0316, but you have 3162, so it exceed the stop band requirement. Therefore, this is the omega C2 will be eliminated. Therefore, omega C1 will be chosen in your calculation. Okay, once you have the omega C selected from the previous calculation, so we have chosen omega C equal to omega C1 equal to 11.1919. Okay, so therefore, to convert the normalized transfer function into actual transfer function, so as referred to the previous slide, so the all s in normalized equation will be transformed into new final equation by s over omega c. So s over omega c, in which s divided by 11.1919. Okay, so finally you write your final transfer function hs. Okay, no more small letter n. Right, so you can simplify the equation if you want, or you can just leave it like this, okay, for your final transfer function. Okay, lastly, the circuit realization for Butterworth filter. Okay, as mentioned earlier, due to the complexity, so the circuit realization for Butterworth will not be discussed in details in this course. However, if you need to come up with the filter circuit, so it's basically more or less the same step as the Chebyshev. You need to refer to the table and then just follow the sequence. Okay, the sequence either by having inductor input or capacitor input. Okay, don't forget to put in all values into the circuit. Okay, with that I end today's session. This is basically the end of this chapter 6. So later in the next session, I'll upload and share more examples related to chapter 6 for your self-study and reference. Thank you.